Hi, welcome to chapters 6 and 7, which are combined together in this lecture on thermal energy, heat, and temperature. So let's start our discussion about thermal energy by doing a little demonstration here, or an activity actually. Go ahead and rub your hands together like is shown here. What do you feel on your hands? So your hands start to get warm, right? So the question is, where does this energy come from? Well, it comes from the friction between your hands. The friction is generating thermal energy. Another thing we can think about is an activity here which is shown in this animation. Suppose we take a book and slide it across the table. The book starts out with a lot of kinetic energy, but then the book slows down and comes to a stop. And again, this is due to friction. The question is, where did the book's kinetic energy go? We learned that energy can't be created or destroyed. It can only change forms. So what's happening here is the initial kinetic energy of the book is being turned into thermal energy. Just like when you rub your hands together, you're generating that thermal energy from the work that you're doing. So this is a new type of energy for us called thermal energy, or E with a little TH for thermal. Thermal energy is the total amount of energy inside a substance due to the kinetic energy and potential energy of all the atoms wiggling or vibrating. Now, like all types of thermal energy, all types of energy, thermal energy is measured in units of joules. So let's look a little bit more now at the details of where thermal energy actually comes from. We said it's the total amount of energy inside a substance due to all the kinetic energy and potential energy of the atoms vibrating. If we take a look at a solid object, we can model the object as a bunch of atoms or molecules connected together by bonds. And it turns out that these bonds that connect the atoms together, by the way, the atoms are represented by these blue spheres here, and the bonds are represented by springs because the atomic bonds actually behave like springs. They can be compressed or stretched, and they store elastic potential energy. But because of these springy bonds between the atoms can wiggle around and vibrate. So this is, the bonds are actually invisible. They're due to electrical forces. So the atoms actually looks maybe something more like this in a solid, where they're all sort of held in place by these bonds, but they're able to wiggle and jiggle back and forth. So this would be a model of any solid object, like a solid piece of iron or a solid block of copper, or even a hard solid like diamond would be represented by atoms connected together by bonds. So next, let's take a look at a couple of video simulations of, so you can get a good picture again of what thermal energy is, and also we'll take a look at the friction activity where we had two surfaces rubbing against each other. This is a computer program or model that simulates the motion of individual atoms inside of a solid. It's very convenient for getting a nice graphical picture of what thermal energy looks like. So in this canister here is a chunk or a crystal of argon. And argon is normally a gas at room temperature, but at very cold temperatures it freezes. And so this thing is set up right now to have a temperature of 1 Kelvin. Now that is only 1 degree above absolute zero. So this is about 450 degrees below 0 Fahrenheit. So at this temperature, argon is ice. It's a solid. And furthermore, all these little circles here represent individual atoms of argon that are held together by bonds. And you can see that, even at this cold temperature, they are slowly wiggling back and forth if you look real carefully. But basically at this temperature, there's very little, if almost no, thermal energy in this crystal. Now what we can do here is I can grab the heater down here and I can raise the temperature a little bit. So now you see the temperature went up to 10 kelvins. And so now, even though it's still a very cold chunk of argon ice, you can see that the individual atoms are wiggling and jiggling back and forth. This is thermal energy. So this piece of argon ice has more thermal energy than the other one did because of all this motion and jiggling of the atoms. And we can, keep adding more heat. We can go up to, this is 25 kelvins now, and you can see that they're really shaking around a lot. In fact, this is starting to become unstable, and if we keep adding more thermal energy, there will be enough thermal energy where the bonds actually start to break, and now you can see the atoms sort of slipping and sliding past each other. We're now into a liquid state. So we'll look at the phases of matter later in this course, but for now we just want to get a good picture of what thermal energy means. This is another computer simulation program that attempts to show how friction creates thermal energy. So the situation here is we've got two books down here, a chemistry book laying on top of a physics book. And in this picture up here, this is sort of a model of what the surfaces of these two books look like. So the chemistry book atoms are shown up here in blue, and the physics book atoms are down here in the green. So right now you can see that there's not a lot of thermal energy here. The individual atoms, you can see them wiggling back and forth a little bit, but basically there's not a lot of thermal energy. Now I can grab the chemistry book and I can bring it down in contact with the physics book and actually start rubbing it back and forth. And you can see as I do this, notice the thermometer, the temperature is going up, and we're creating thermal energy. So the motion of these of the atoms has increased due to the physical contact of them rubbing into each other, and that agitates the atoms and gets them moving faster. We're creating thermal energy, and what we would actually feel is that, when we rub these two surfaces together, just like when you rub your hands together, you would feel warmth, you would feel heat generated. So this is, again, what thermal energy is all about. Let's now talk about temperature. We saw in the computer simulation that when we added thermal energy to the solid block of frozen argon, the atoms started wiggling around faster, and we noticed that the temperature increased. So temperature is actually a measure of the average kinetic energy per atom or molecule inside an object. Temperature is measured in units of degrees. So you're probably most familiar with degrees Fahrenheit. So when you look on at the weather forecast and it says it's going to be 76 degrees today, that is usually almost always Fahrenheit temperature. But there are other temperature scales used as well, the Celsius scale or centigrade scale, degrees C. And then what scientists like to use is the Kelvin scale, which is denoted with a K. We'll talk about those a little more detail in the next slide. For now, though, it's important to understand what temperature means. Basically, from our definition here, that temperature is a measure of the average kinetic energy inside the substance. High temperature means the substance has lots of kinetic energy, and likewise a low temperature means there is a less amount of kinetic energy. So if we take a solid, for example, remember a solid, we can consider it as a bunch of atoms held together by bonds. That's what makes it a solid. But those atoms are wiggling and jiggling. So at low temperature, a solid could be represented by this animation here. And then if we take that same solid and raise it to a higher temperature, notice, the same atoms are there, but of course now they're wiggling and jiggling a lot more vigorously, and therefore they have more kinetic energy, and that gives the solid a higher temperature. So the only difference between a high temperature object and a low temperature object is just the amount of energy of those atoms inside the substance wiggling and jiggling. And for gas, it's sort of a similar type concept. A gas at a low temperature has, this time the gas atoms or molecules are flying around independently. They're no longer bounded or bonded together as they are in a solid or liquid. Now they're free to move about, but at low temperature, they're moving at relatively slow speeds. And if we increase the temperature, by placing a flame under this container of gas, we see now the gas atoms are moving around much more quickly. They have more kinetic energy. This raises the temperature of the gas. Let's now turn to lowering the temperature of solids until basically we get to the coldest possible temperature, which is called absolute zero. So imagine we have a solid, for example, a solid chunk of iron or something like that, and we start cooling it down inside of some sort of cryogenic freezer. Well, as we get it colder and colder, remember what we're doing is we're removing thermal energy from the solid. So we can see that the atoms are wiggling and jiggling, but they're barely moving, right? We can just barely see them moving. So if we can keep reducing the temperature and removing more and more thermal energy, we can, at least in theory, get to a point where all of the thermal energy of these atoms is gone. And at that point, this solid here, these atoms inside the solid, will be absolutely still. They will not be moving at all. So this is a temperature called absolute zero. It's a temperature on the Kelvin scale at which the atoms have lost all their thermal energy. And so on the Kelvin scale, this is 0 kelvins. And this is why scientists like to use the Kelvin scale, because it starts at 0 and it just goes up. On other scales, for example, the Celsius scale, absolute zero is minus 273 degrees Celsius, or minus 459 degrees Fahrenheit. By the way, the Kelvin is named after Lord Kelvin. Okay, so one question that comes up here. Remember, we've got this thing in some kind of a super cryogenic freezer to get it as cold as possible. The question is, can we keep cooling down this piece of material to get below absolute zero? In other words, can we crank up the, crank the temperature dial to make it even colder than absolute zero? What do you think? Would that be possible? And why or why not? Well, the answer to this is no. We can't get a temperature below absolute zero, because remember what the definition of temperature is. Temperature tells us how much average kinetic energy is in these atoms. So at absolute zero, we have reduced the kinetic energy to 0. They are not moving at all. So that is by definition the lowest possible temperature that is possible. So we've been mentioned the 3 temperature scales briefly, and I just want to show a little bit more explanation. So the 3 common temperature scales that you see and hear about are the Fahrenheit, Celsius, and Kelvin scale. The Fahrenheit scale, which we use for the weather forecasts and things like that, is set up so that the freezing point of water is 32 degrees and the boiling point of water is 212 degrees, and room temperature is somewhere around 70 degrees, somewhere between 68 and 80 degrees. Absolute zero, by the way, on the Fahrenheit scale is about minus 460 degrees Fahrenheit. Now the Celsius scale is set up differently. It's set up such that the freezing point of water is defined as 0 degrees Celsius, and the boiling point of water is defined as 100 degrees Celsius. On this scale, absolute zero is negative 273 degrees Celsius. Now, the Kelvin scale, which is the scale that scientists typically use, starts at 0. That's absolute zero here, and temperatures just go up. For example, room temperature is around 300 kelvins. So we will be using various temperature scales as we work through this chapter. Converting between Celsius and Kelvin is actually quite easy. To get kelvins, you just take the Celsius temperature and add 273. Likewise, to get the Celsius temperature, you just take the Kelvin temperature and subtract 273. So we've seen these 2 concepts, temperature and thermal energy, And they are definitely related to each other, but they are certainly not the same thing. Just to summarize, remember temperature is an indication of the average kinetic energy inside of a substance for each atom, whereas thermal energy is just the total amount of energy inside a substance. So there, in that sense, we have to add up all the kinetic and potential energy of each atom. So let's just go through, this is sort of a conceptual quiz here. For each of these pairs of items, let's try to think about which item has the higher temperature and which item has the greater thermal energy. So for example, let's start with this one. If I show you a hot potato and a cold potato, which one of these has higher temperature? And then think about which one has greater thermal energy. So go ahead and pause the video and think about that, and let me know, or remember your answers. Okay, so in this first one, it's pretty basic. Obviously, the hot potato has a higher temperature because it is hotter, okay? And likewise, the hot potato has more thermal energy than the cold potato because if we added up all the energies of all those atoms inside the potato, the hot potato would certainly have more thermal energy because remember, each of those atoms is moving around faster. It has more kinetic energy. So this first one was kind of an easy one to get us started. Let's now look at this one. Let's compare a hot potato versus a cold lake. So what is a cold lake? Well, think of like a lake in Canada in the winter where it's got ice on top and the water temperature is barely above freezing, right? You wouldn't want to stick your feet in it. It would hurt your feet. It's so cold. So let's compare these. Go ahead and pause the video and think about which one has more higher temperature and which one has more thermal energy. Okay, so for temperature, again, this is pretty simple. The hot potato, which comes out of your oven, might have a temperature of, let's say, 350 degrees Fahrenheit, right? The temperature of your oven. The cold lake, on the other hand, might have a temperature of maybe 35 degrees Fahrenheit. So the hot potato certainly has much higher temperature than the cold lake. But what about thermal energy? Well, it turns out that the cold lake has much, much more thermal energy than even the hottest potato you could imagine. And the reason for this, remember that thermal energy depends on the total amount of energy inside the object. So a lake has so much mass, it has so many more atoms compared to a tiny little potato, that the lake is going to have a huge amount of thermal energy, even if the lake is very cold. All right, last one here. Big hot potato versus small hot potato, and assume that they both came out of the same oven. So go ahead and pause the video if you want and think about the answer to this one. All right, well, so if these two potatoes were both inside the same oven, then their temperatures would be equal. Neither one of them has a higher temperature, right? The temperatures are the same. However, for thermal energy, the big hot potato would definitely have more energy, more thermal energy than the small hot potato, just like the cold lake did here. The reason here is that the larger hot potato has more mass, it has more atoms, therefore it has more total energy, which is thermal energy. Let's now turn to the concept of heat. So what happens if we place a hot block of metal against a cold block of metal? So this is our hot block of metal, just came out of a furnace or an oven, so it's maybe glowing red hot. And then here's a cold piece of metal that maybe we had in the freezer. And we actually stick the two pieces of metal together so that they're touching. Well, what happens here is, remember what temperature means. High temperature just means the atoms are wiggling and jiggling and shaking more, whereas cold temperature means they're relatively still. There's not a lot of kinetic energy. But these hot atoms in the hot piece of metal here, because they're they're vibrating so violently, they are banging into the cold atoms here and causing them to start vibrating and shaking. All right, this is a physical transfer of thermal energy from the hot to the cold. So this brings us to the concept of what physicists call heat, which is abbreviated by Q. Heat is thermal energy that's transferred from one object to another, or between a system and its environment, due to temperature differences. So since heat is sort of, you can think of it like the flow of thermal energy, the units of heat are joules, which is the same as thermal energy. The other thing that this little demonstration up here, animation, shows is that heat only moves from hot to cold, because remember what high temperature is, or what thermal energy is a lot of motion of these atoms. And so that will always transfer from atoms that have a lot of motion. They will pass on that motion to ones that have less motion, meaning the heat can only go from hot to cold. It can't transfer from cold to hot. Speaking of heat, there are 4 heat transfer mechanisms that are basically methods or mechanisms to get heat to go from one place to another. So the first one, this is the one we actually were just looking at on the last slide, is called conduction. That's shown in this one here. Conduction is when there's direct contact between two objects. And remember, those atoms inside the hot piece of metal, or whatever the material is, are banging against the cold atoms in the other material and causing them to start moving, which raises their temperature. So thermal energy is transferring from hot to cold by direct contact. That's what conduction is. Now, convection is different. Convection is when you have heat being transferred by a warm fluid, such as a gas or a liquid. And this is something that is common, for example, when you see hot smoke rising from a fire, or when you boil a pot of water and you see the water starting to churn before it boils. You'll actually see convection currents as the warm or hot water expands and rises up above the colder water. The third type of heat transfer mechanism is called radiation. And this is when you have a hot object that actually radiates heat through the form of electromagnetic radiation. Now, we're going to talk about electromagnetic radiation in a little more detail later in the course when we talk about light and the electromagnetic spectrum. The fourth type of heat transfer mechanism is one that you're familiar with, and that is evaporation. Evaporation is the process where a liquid evaporates, or basically turns into a gas or vapor. And the way it does this is only the most energetic atoms can escape the liquid. And so those are the ones that have the most thermal energy. So evaporation is a process where basically the highest thermal energy atoms are selected, and they leave the material down here, the substance, like if this was water, for example, and this is a cooling process because we're getting rid of the atoms that have the most energy. Let's take a look at heat conduction, just a little more detail. Remember, conduction is heat transfer by direct contact between objects. Heat flows from hot to cold. So, if we have the metal frying pan over the fire, obviously, you don't want to grab the handle here if it's not insulated. So what's happening here is that thermal energy, which is coming from the flame down here, is causing these iron atoms to vibrate and wiggle, and they bang against their neighbors, and that heat transfers up the handle till it gets hot. And that's sort of shown over here in this animation. You can see the heat starting here on the left, and it's moving to the right because these atoms start wiggling and jiggling more. This is the transfer of thermal energy, which is called heat. Let's now turn to the 3 phases of matter. The 3 phases of matter are solid, liquid, and gas, which are shown here in these diagrams. We're going to look at a computer simulation that will help explain these phases of matter much more better, much more clearly than can be seen on these diagrams here. But this is related to thermal energy and heat transfer, because what happens here is when we add heat or thermal energy to a solid, we can cause a phase transformation and basically melt the solid into a liquid, and then by adding more heat we can turn the liquid into gas. So we'll look at this in the video simulation next. This is a computer simulation that demonstrates the states of matter. So what I've selected here is the atom argon, or the element argon, which is normally a gas at room temperature, but we're going to start here with our argon sample at a very low temperature. You can see that we've got it set to 2 kelvins, which is only 2 degrees above absolute zero. That means that the temperature here is about 460 degrees below 0 Fahrenheit. So at this low temperature, you can see the argon here, which is represented by these little pink spheres here, are the argon atoms. They're all connected together solidly, and so this is the solid phase of argon. So this is argon ice, basically. You can see that there's a little bit of thermal motion. You can see the molecules are wiggling around just a tiny bit, but they are held in place rigidly by the bonds between the atoms, and these atomic bonds are very strong at this temperature. It makes this a solid object. So what we can do here is add some heat to our ice crystal here. So you can see the temperature is now up to 20 kelvins. We still have a solid phase here, but notice now there's some more thermal energy added to our ice crystal, and the little atoms are wiggling around more vigorously now. So now as we keep adding more heat and thermal energy, we see something start to happen. Some of the atoms now have enough energy that they actually break apart from their neighbor. So this is what's happening here, is melting. We're starting to see the solid break apart, and some of the atoms are able to slip and slide. So as I keep adding a little more heat, we're going to enter the liquid phase of the argon. So now you can see that the argon atoms are completely slipping and sliding past each other. There's no more shape to this piece of argon. It's no longer a solid. We have entered the liquid phase. One thing you can also see here is that occasionally one of these atoms gets enough energy to actually get kicked right out of the liquid. And so this is evaporation starting, and this is going to increase as we keep adding more and more temperature. So let's go ahead and raise the temperature more and heat up this liquid argon. So we're seeing more and more activity now by the atoms. So look what's happening now. We've got the argon atoms have so much energy that they don't even stick together at all anymore. They're all flying apart separately. We have now formed argon gas, right? This is the gas phase of the argon. And we can go back. Oh, and let me just keep adding. I'll keep increasing the temperature. As I keep raising the temperature, you can see we're now up to about 280 kelvins. That just means there's more and more motion of these atoms. They're going faster because, remember, that's higher temperature, just means faster motion of the gas atoms. We can go in reverse. Let's you can see me adding the ice down here at the bottom, and we can bring that temperature back down. And let's see what happens here. Notice that now that the atoms are slowing down, some of them are starting to actually stick together a little bit occasionally. And as we lower the temperature, you'll see more and more of them start to stick together. So they don't have enough motion now to break apart from each other, and their attractive forces to each other are starting to cause them to clump together. This is, we're having what's called condensation here. We're going from the gas phase back into the liquid phase. And so now here we have our liquid phase, where the argon atoms are down here and they're basically slipping and sliding around each other. And if I keep lowering the temperature even more, we solidify the liquid. Now notice the atoms are actually bound to each other, and they're not really moving apart anymore. They can't slip and slide past each other. We've formed another argon ice crystal. Let's now turn to something called specific heat, or it's also known as heat capacity, or sometimes specific heat capacity. It all depends on the textbook that you're using. Let's ask a question here. Suppose we transfer 500 joules of heat to a kilogram of water. That's a liter of water, by the way, a kilogram. Now what will happen? Well, obviously the water is going to warm up somewhat, right? We're adding heat to the water, so its temperature is going to increase. The question is, how much will its temperature increase? By how many degrees? We would like to know this. Then another question comes up, what if we transfer this same 500 joules of heat to a kilogram, in other words, the same amount of copper? Will its temperature increase be the same? And the answer to this second question is no. The temperature increase will be different because water and copper respond differently when heat is transferred to them. And so this leads us to what is called the specific heat of a substance. And the specific heat is abbreviated by just the letter C. The specific heat is a measure of a substance's thermal inertia, or more technically, its resistance to temperature change when heat is added. So the real formal definition of specific heat, C, it's the amount of heat in joules needed to raise 1 kilogram of a substance by 1 degree Celsius. So sort of the idea here is if we have two substances here, two different materials. One has a high specific heat, high C, and the other a low specific heat, low C. And we add heat. Remember, heat is Q. So we're adding heat to both of these. Well, the material with a high specific heat will undergo only a small delta T, a small change in temperature, whereas the material with low specific heat will undergo a large change in temperature. So high specific heat means this material has a lot of thermal inertia or resistance to temperature change. It can absorb heat without its temperature changing much. We'll next look at a video simulation demo to show the specific heat of different substances. So this is a simulation tool that simulates the effect of specific heat. So on the left here is some material that has a small specific heat. So for example, this would be any metal has a relatively low specific heat. On the right is a block of material with the same mass as over here, but it has a large specific heat. So this would be a substance, for example, water has a very large specific heat. So let's go ahead and notice they're both starting here at room temperature, 20 degrees Celsius. And underneath each of these, we're placing a source of heat. So it's a little lamp or flame that's going to add heat. So as you can see, once we turn on the fire, we can see the thermal energy start to increase as these things heat up. But notice that the material over here with the small specific heat is changing temperature much more rapidly than the material over here with the larger specific heat. So we see the metal over here is heating up more compared to the water over here on the right side. And as we keep running this, you can see the simulation is also showing the material over here on the left side, a lot of thermal energy, a lot of motion of the atoms, and over here on the right side, relatively little. So specific heat is a value that depends on the material, and it's something that we don't memorize. We just look it up in a table to see what the value are. So this is basically a short table of the specific heat of some common substances, liquids and solids. And what's interesting is at the top of the list here by far is just plain old ordinary water. It has a very, very high specific heat of 4,190, and the units are joules per kilogram per degree C. So what this means, remember the definition of specific heat. If we have 1 kilogram of water, now a kilogram of water again is 1 liter. So this is like, one of your hydration flask type a liter bottle of water. It would take 4,190 joules of heat to raise the temperature of that water by just a single degree, which you wouldn't even probably notice the temperature change. So water can absorb a lot of heat, and we'll talk about it a little bit more in the next slide. The human body is, of course, made mostly of water, so it's not a surprise that our bodies also have a relatively high specific heat, and this is a good thing for temperature regulation. When we go out into the hot sun or go hiking in the desert or whatever, this high specific heat keeps our body temperature relatively stable. We can absorb a lot of heat from our surroundings without our temperatures increasing. And then you can go down the list here and see these other materials have lower and lower specific heats. What's kind of interesting is down at the bottom here are the metals. We see iron here, copper, silver, and lead are all very low specific heats, especially compared to water. They're more than 10 times less than water. So to go back to our original question on specific heat, if we add heat to water and to copper, what happens is the copper is going to get much hotter than the water, because the copper has a very low specific heat, 385, compared to the water's high specific heat. So let's just briefly talk about water's high specific heat again. So remember that it takes 4,190 joules of heat to raise 1 liter or 1 kilogram of water by 1 degree C. This means that water can store lots of heat inside its molecular bonds without getting hotter. And this is a good thing. Water, with its high specific heat, makes it ideal for living organisms. We talked about the heat regulation, for example, in our human bodies, are comprised mostly of water, and therefore this gives our bodies protection against absorbing heat without overheating. Water is also very good, obviously, for putting out fires, and this is, again, because water can absorb a lot of heat before it boils away. And then water is an excellent coolant for car engines, nuclear reactors, other industrial processes, and so forth. Again, because the water can absorb a lot of thermal energy without its temperature going up very high. So now we can address the question. If we add heat to an object, how does its temperature change? And this is summarized by what is called, or at least I call it, the heat-temperature relation. So the heat-temperature relation says that Q, remember Q is the heat added to the object in joules, is equal to the product of the specific heat of the object, C, the mass of the object in kilograms, and delta T, which is the temperature change of the object, either in degrees Celsius or in kelvins. So this relationship here, Q equals Cm delta T, is very useful. It tells us basically what the temperature change will be here if we add heat to an object here. And we can, of course, solve for, this equation for either Q, or we can solve it for delta T. Let's see some examples where we use this. So here are 2 examples of using the heat-temperature relation. The first one says how much heat must be added to a 0.5 kilogram block of copper to raise its temperature by 10 degrees C. So imagine taking this block of copper here and setting it on a hot stove or a hot plate. So obviously the heat Q is going to flow from the stove into the copper, and the copper is going to heat up, right? Its temperature is going to increase. We want to know how much heat, Q, we should pump into this copper here to get its temperature to go up by 10 degrees. So using our heat temperature relation, Q equals Cm delta T, first of all, we look back in that table and we find the specific heat for copper is 385 joules per kilogram per degree Celsius. The mass of the copper was given here as 0.5 kilograms, and the temperature change is 10 degrees C. So by multiplying 385 times 0.5 times 10, we end up with 1,925 joules. And if you look carefully here, you can see the units, the kilograms here cancels those kilograms. The degrees C here cancels these degrees C, and we're left with just the joules here, which is the unit for heat. In our second problem, how much colder does the copper block get if we place it on ice and remove 1,000 joules of heat? So this time, let's take our block of copper and let's set it on a block of ice so that now Q is going to flow from the copper to the ice. Remember, heat always transfers from the warmer object to the colder object. So this time, what we're asked to do is figure out what is the temperature change. In other words, how much colder does it get? So we're going to take our equation up here, Q equals Cm delta T, and we're going to solve for delta T. Well, that's easy. We just divide by C and divide by M. So delta T is equal to Q over Cm. Now, what is Q? Q is the amount of heat that's added to the copper, but we're not adding heat, we're removing it. So the heat is flowing away from the copper. So we put a minus sign in front of the number of joules. So we're removing 1,000 joules of heat, so Q is negative 1,000. Again, this is the same copper with the specific heat of 385, so that's the number there. And then the mass is the same block of copper, which was given up here at 0.5 kilograms. So we have 1,000 divided by 385, and 0.5 multiplied together down here. And that will give us a temperature change, delta T, remember we're solving for, of negative 5.2 degrees C. Where did this minus sign come from? Well, it came from right here. So what does this minus sign tell us? This tells us that the temperature change was negative, meaning the copper block got colder by an amount of 5.2 degrees Celsius. Okay, let's do a problem here that involves a couple concepts, and we can put these all together. This is where we have a temperature increase due to friction. And so before we get into this problem, it turns out that whenever there's friction present, we always generate thermal energy. And this is something that we saw at the beginning of this chapter when we talked about rubbing our hands together to make them feel warm, or we slid a book across the table and we generated, the friction generated thermal energy there as well. So in this problem, suppose you're driving your 1,500 kilogram car at 60 miles per hour, which converts to 27 meters per second, and you apply your brakes, coming to a complete stop. How hot do your brakes get? So we're going to assume your brake discs are steel and they have a total mass of 20 kilograms. So the way brakes work, without getting into a lot of detail here, is your car, if it has disc brakes, it has this steel disc basically mounted on your wheel, and when you press your brake pedal, these brake pads here squeeze against the disc here, and they rub, and they just create friction. And what this does is it transfers the kinetic energy of your car into thermal energy, into heat. So the first step to solve this problem is to compute the kinetic energy of the car, which will be converted to heat via friction. So the total kinetic energy of the car, remember kinetic energy is 1/2 mv squared. So we have 1/2 times the mass of the car is 1,500 kilograms. The speed of the car was 27 meters per second, and remember that's squared. So it comes out to be quite a large number here, because we're talking about a car, 546,750 joules of kinetic energy. Now that's before you put on your brakes. What happens to all this kinetic energy when you put on your brakes and come to a stop? Well, remember, energy cannot be created or destroyed. So this energy does not go away. It just converts into heat, into thermal energy. So this is going to be our Q. this amount of heat we're going to assume is all transferred to the metal discs on your car. And there are, 4 of these brake discs, 1 on each wheel, we're told the total mass is 20 kilograms. So step 2, we're going to find the temperature change due to heat. So remember that, from our temperature heat relationship, when we solve it for delta T, we get delta T equals Q over Cm. And Q is this number right here, 546,750 joules. We have to look up C, the specific heat for steel, and I found that to be 460. And then remember the mass, the total mass of the brakes was 20 kilograms. So this big number divided by 460 and also divided by 20 gives us 59 degrees Celsius. And this is an increase of over 100 degrees Fahrenheit. So if the brakes started at room temperature, we're talking about a final temperature, of something like 170 degrees Fahrenheit, which is quite hot. Here's another problem that's kind of interesting because it demonstrates several of the concepts that we've learned about energy and now thermal energy and heat. And you're also going to do the details for this problem in the homework. So let's just talk about the concepts here so that when you do this problem in the homework, you'll kind of understand what's happening. So the question is, what happens to the temperature of an object if it drops to the ground? So to answer this question, let's think about taking an object like a rock, let's say, and let's say you lift it up over your head. Before you drop it, the question is, what type of energy does it start with? What do you think? Well, maybe you got it right. This rock has potential energy up here, right? Gravitational potential energy. Now, when you drop the rock, what happens to that gravitational potential energy? Well, remember from our last chapter on conservation of energy, that potential energy is converted or transferred to kinetic energy as it picks up speed and falls to the ground. So right before the rock hits the ground, all that potential energy up here has been converted to kinetic energy of motion as it's falling. Now the question is, what happens to this energy after it hits the ground? Because this rock lands on the ground and all of a sudden it's not moving anymore. So the question is, does that kinetic energy just disappear? Does it get destroyed? Well, we know it can't, right? The conservation of energy principle tells us we can't destroy energy. We can only convert it to a different form. And so the form of that energy is ultimately a temperature increase. Now there is some energy released with sound and the vibrations in the ground and so forth, but most of the energy that started up here will end up as thermal energy, which means the rock and the ground that it hits will be slightly warmer. So again, you'll look at this in the homework and you'll get to work this problem out with some numbers. The last problem where we had a rock falling and we said that potential energy basically ends up being thermal energy, well, that we can sort of take that to the extreme, and this leads to an explanation of how stars form, which is kind of interesting. And this is something we'll be talking about in more detail later in the course when we do our unit on astronomy. But basically, kind of in summary, the way stars form is it starts with a rotating gas cloud that has the mass of anywhere from 10 to 1,000 suns. And because of all this mass, of all this gas and dust, this gas cloud starts to contract due to its own gravity. So because of all the mass of all those potential stars in this cloud of gas, there's a lot of gravity. And this gets this gas cloud to contract. This is an actual image of a dark cloud of dense gas and dust in space where stars are starting to be born inside. So what happens as this thing starts to contract is it flattens into a disk, and the center of the disk gets hotter as gravitational potential energy is converted into heat. So in the center of this disk here, where the density of the gas is the highest. This gas is getting compressed. And again, this all started as gravitational potential energy, and now we're ending up with a lot of thermal energy. And this is called a protostar. This is like a pre-birth state of a star. So the central region here will become denser and hotter. And this is actually an image here. You can see the protostar inside of the remaining disk of gas and dust around it. When the core temperature reaches approximately 5 million kelvins, it's sort of like a magic trigger threshold temperature. Nuclear fusion can start, and hydrogen fuses into helium. And we'll learn about this more when we talk about nuclear physics later in the course. But this is when a star is technically born and starts to shine on its own. So that the energy that basically got the star hot enough so that it could start to shine was originally gravitational potential energy. And that is the end of our chapter here on thermal energy, heat, and temperature. I will see you guys for the next chapter soon.